UCSD 111, lecture 13, we're going to talk about number systems. The discussion of the number systems is very important, in particular if you have operations that use floating point. And this happens to be the case with a lot of modern algorithms. Like, for example, in a lot of machine learning or signal processing, we need precision, and then fixed point numbers may not be able to provide all the precision that we're looking for. In the project that we have for the course, you're not using the number systems, but I think it's really important because most of the people who take this course want to go and get a job in a real company or get exposure at a later time. If you haven't seen the number systems, you may actually have a harder time digesting all what is happening. But today's lecture is really meant to make this more digestible, more understandable, and also numbers are really fundamental to the understanding of the world, and also understanding how computers evolved and how computing and calculation. So let's look at the brief history, what has been happening. So we just want to look at historically what has been happening for, like, in terms of coding for numbers. Number systems were used by Egyptian, and I mean, maybe they have been used before then, we don't know, but we know about 4,000 years before Christ, we had numbers that were kind of sums of symbols. So if you had, for example, a 34, this is how you would represent it. Then the Babylonians were actually the people, like, about 2,000 years after that, who looked into positional system, and don't ask me why they came up with a radix 60 number system, and basically this is how they would compute a number. May not be the most straightforward, but they somehow had this notion of holy things, and 60 was a good number or a lucky number for them, so they started using it. But what is important here is that the numbers were actually showing position. So, the numbers here are showing, a position that is less significant than the middle one, which is a higher significance than the larger one. So they actually got to scale things up very well. Believe it or not, a notion, or an explicit notion of the zero, didn't exist for many years. This is credited to the Babylonians. So they introduced a new symbol for zero, and then they kind of were able, after they introduced zero, they were able to talk about fractions. Sorry, this slide is a little messed up. We'll change it in the actual representation. Here, then there's the Roman numerals, which probably you guys have all seen. It doesn't look very straightforward. It doesn't look very intuitive. It is, as I'm sure you guys have seen it on the clocks mostly these days, not on many other places. But as you could imagine, as the number system is not very intuitive, doing computation and doing arithmetic with that is actually super difficult. So this is something that they were trying to use, and it also exists in many of the Roman numerals, but this actually is not being used. The number system that actually we use today is being invented sometimes like about 3,000 years ago in India. It's a Brahmi numeral. And it is basically, it defines digits for numbers from 1 to 9 and then 0. Now, you see how things evolved. So this was like the original way how it was shown. So 1, 2, 3, 4, 5, and 6, and so on. And now you see how it kind of got translated into different scripts from different nations, and it's shown differently. So this is the kind of Roman way, how it's kind of interpreted over the years. This is how it is interpreted in Arabic countries, and so on and so forth. So this is the number system we're using today, and the radix 10 is really kind of the position code decimal system, which we're really using today. As there is some evidence that it has been used in 9th century, and this is the number system we're using today, of course, and you guys all know about this. And it's kind of interesting to know that zero did actually not spread so fast from where it was originated, like before Christ, to like about 750 AD to other places. In Europe, it was not until 1250. Of course, we are talking about different era and different speed of communication, but as you all know, zero is super important. It enables a lot of new arithmetic, and in particular, fractional arithmetic. It improved many things. Now, imagine that you have these number systems that are modern, and you all know about them, and you know about integers, which are positive and negative. And then the negative numbers, as you probably have seen in your logic design course, you could actually show that with two's complement system or with the sign systems. But what becomes important in a lot of scientific computation are fractional numbers. And you could also even show, as you will see shortly in this lecture, you could also show huge numbers with fractional numbers. But the numbers with fraction, they could be fixed point, meaning that you're only allowed to have a certain number of bits after your fraction, and that binary point is fixed. Or you could have a floating point. You could represent basically any number, all the binary points float to the right of the most significant one. And then, you could have a representation system based on that. Here, I'm showing just a representation of some examples of how you could actually encode numbers in limited number bits. Here we have 4 bits. So if you're using the 4 bits to just represent numbers from the 0 to 15, you would be able to do that. But if we have a sign, we allocate one of the bits for sign, but we just have sign magnitude number, which means that the first 3 bits are the magnitude, the last bit is the sign, and then a 0 means negative, a 1 means positive. Then as you can see in the system, 0 has 2 values, which is shown here. We may have a fixed point, meaning that we have 3-bit numbers, and then a 1 bit is assigned for the fixed point, and so on and so forth. We're gonna talk about this. But as you see here in the floating point case, the distances between numbers are not uniform like they were here in the system. And this is basically a logarithmic scale, which allows us to scale with the number of bits we can represent bigger number. And this is sometimes very useful because we may want to have a larger number of numbers to deal with. One important thing to know is that no matter what kind of system you use, you will have a finite number of finite representation, because the number of bits on your computer is finite. It's just that as we go to floating point representation, we are able to go to the logarithmic scale, which gives us many more possibilities. Okay, so